Okay, so today we're going to look at redshift, but before we do that we have to understand some fundamentals about how light travels and what makes up the white light that the sun produces. So here's our star, the sun. Now the light we see coming from our star is predominantly white light. It travels as a transverse wave from the star to our eyes, but that white light is actually made up of lots of different colours. It's actually made up of the spectrum of colours of the rainbow, so from red all the way down to violet. When we look at the sun, we tend to think of it as being orangey yellow, but in fact all the light coming from the sun is made up of these colours. In fact, that's what gives different objects different colours, but that's another lesson. Here in closer detail are the wavelengths of different colour lights broken up into their measurements. We can see from the top the red wavelength is much greater than the green wavelength, which is also greater than the blue wavelength. So each colour in the colour spectrum has its own unique wavelength, and this is important when we go on to understand redshift. Here is our sun again. Our sun is like many stars, so we're going to use this as an example. We know that our sun is fixed in a position with Earth. So although the sun in a minute will move across the screen, it doesn't mean our sun's going to do that, and we'll talk about why that is in a second. Now because our universe is expanding, objects around us are moving away from us or towards us. When we view them, their light pattern changes. In space, when objects that give off light move away from us, the wavelength of light is more stretched and therefore corresponds to the red side of the spectrum. If a star or object that gives off light is moving towards us, the opposite effect happens. The wavelength of light is closer to the blue end of the spectrum, with a much shorter wavelength. To understand why this is, we can use a different example. Here is an ambulance. When an ambulance turns its sirens on, it produces sound, and those sound waves, when stationary, have an even distance between them, like the diagram here. As the ambulance starts to move though, those sound waves are compressed to the front end of the ambulance and spread out more at the back end of the ambulance. We call this the Doppler effect. The Doppler effect applies to light waves as well as sound waves. When something giving off light is moving towards us, the waves at the front compress. When something is moving away from us that gives off light, the wave at the back spreads out. But how can we see these changes in wavelengths? If we were to look for a special instrument, a star, called a spectrometer, that can tell us a lot of information about the object that we're looking at. It tells us the composition of the object, i.e. what the star is made of, or what the galaxy is made of that's giving off light. A spectrometer, when analysed, produces a pattern like this. We can see some lines on this diagram, and they are called absorption lines. They exist because whatever we're looking at absorbs the wavelength of light of those elements. Now to analyse whether something is moving away or coming towards us, we have to look at these lines to see which end of the spectrum they are shifted towards. Let's take a look at some examples together. Here we have 5 examples. At the very bottom we've got a laboratory reference which is very similar to our star. Above that we have another star that's close to our sun. Then we have a nearby galaxy, a distant galaxy and a very distant galaxy. We can see it's as we go up the spectrographs that the lines start to shift in one direction. They're moving towards the red end of the spectrum. So all the objects here are moving away relative to us. But which one has the greatest redshift? Well, it will be this top one here. We can use any lines in a spectrograph to take reference from. In this example, they've taken the reference line to be the fourth line in. i.e. they're not looking at all the lines, because if you notice the top one, some of the lines have then dropped off of the other end of the red side of the spectrum. So calculating redshift is about understanding these spectrographs. If the lines are shifted towards the red end of the spectrum, there is greater redshift. And there's another important thing that redshift tells us. That is that the universe is expanding and everything is moving away from everything at the same time. Redshift supports this idea and it's widely accepted in the scientific community.